Okay, in this video we're looking at the more complicated redox titration type calculations. The difficulty really is with these is not so much the calculations of the moles, but it's the explanation at the end, the justification. Okay, you can pause the video and read the question yourself, but for time I'm just going to go on to the main thrust of it, which is manganate ions are oxidizing vanadium 2+ back up to vanadium 5 as a vanadate ion. Okay. The question asks us to prove that vanadium has changed oxidation state from +2 to +5 in this titration. Okay. So the question starts off with ammonium vanadate 5, that's reduced down to vanadium 2+. So what we do know is that the moles of vanadium 2+ is going to be equal to the number of moles in 25 cubic centimeters of 0.1 mole per decimeter cubed ammonium vanadate. Okay, so we will now calculate the moles of vanadium 2+ to start with. Moles of vanadium 2+ is given to us by using an N equals a C times V over 1,000 calculation, which is concentration is 0.100. Note that we've got a precision now of 3 significant figures. 25.0 divided by 1,000, which when you calculate it comes out to be 2.5 times 10 to the minus 3 moles. Okay, the moles of manganate which we used to oxidize the vanadium back, again it's using an N equals CV over 1,000. I'm not going to write down the formula, just going to go straight to the calculation. So our concentration is 0.0500 multiplied by 30.0 cubic centimeters divided by 1,000, which equals 1.5 times 10 to the minus 3 moles. Sorry, is that clearer? Okay. So now we've got our ratio of vanadium 2+ to manganate ions. There are several ways you can approach this proof idea. Probably the simplest way is to look at the number of moles of electrons in the manganate part of the reaction. So the manganate requires 5 electrons per mole, okay, or 5 electrons per manganate ion. Okay, so what we can do now is calculate the moles of electrons used by manganate. So moles of electrons used by manganate ions. Oops. Well, that's equal to our number of moles, which is 1.5 times 10 to the minus 3, multiplied by 5 electrons. So that equals 7.5 times 10 to the minus 3 electrons. Now, those electrons have been released by the vanadium 2+. So this means that so now we know the number of moles of vanadium 2+, so we can now identify how many electrons per vanadium 2 species have been released. So the number of electrons released is equal to the total number of electrons divided by the moles of vanadium. Which equals 3 electrons. So therefore we can see that as the vanadium started off at 2+, it has now gone to vanadium 5+, because each vanadium 2+ has lost 3 electrons. Okay, and that's probably the easiest way to approach this. You can look at this using the ratios, but then the reasoning, well, following it can be a bit more complicated. So for example, the ratio of vanadium 2+ to manganate is 5 to 3, and then you can say, well, 3 lots of manganate requires 5 electrons, that's 15 electrons. 15 electrons divided by 5 from our initial ratio gives you 3 electrons. But again, that's more complicated. Okay, so now we're going to move on to another calculation. Okay, now in this calculation we again have vanadium in the form of a vanadate ion reacting now with sulfur 4 oxide. And this is as a gas. So now we've got 2 different types of moles calculations to be dealing with. The first one for the vanadium again is an N equals CV over 1000. The second one will be using an ideal gas equation. Sometimes it can be difficult to see where you have to go with these things. So I always recommend just go with the calculation first of all, and then try and think about the reasoning. You will always gain marks for your calculation. Okay, so first thing we're going to look at now is the moles of vanadate. So we said that's given by an N equals C times V over 1000, and that is given to us as 0.800 times 50 over 1000, which equals 0.04 moles. Okay. Now, I mean, ideally I should be using the same level of precision given in the question, which is 3 significant figures. Remember that these zeros before the 4 do not counted for our significant figures. Then the moles of sulfur 4 oxide. Now, sulfur 4 oxide is aka sulfur dioxide. Now it's given as a gas, so we know you need to use the ideal gas equation. So PV equals nRT. N is equal to PV divided by RT. Divide both sides by RT. And this gives us, and then we substitute in our values. Now we've got to convert our values into the correct units. So the units are pascals for pressure. So it's 98,000. And then we're going to multiply that by our volume. Now our volume is 506 times 10 to the minus 6 meters cubed. Okay, how have we got that? Well, our volume was 506 centimeters cubed. 1 cubic centimeter up here at the top is equal to 0.01. To get 1 centimeter cubed, you need to cube that 1 times 1 times 1 is 1. To get the cube of 0.01 meters, again 0.01 times 0.01 times 0.01, which equals 1 times 10 to the minus 6. I find it easier just to stick with that in our calculation rather than try and say, well, it's 5.06 times 10 to the minus 4. Do make sure you're comfortable with converting your units. Okay, the bottom line is the ideal gas constant, which is 8.31. We're going to multiply that by our temperature, which is at 20 degrees Celsius, but we need to add that to 273 Kelvin, which is 293 Kelvin to get into the correct units. So then our number of moles, when you calculate it out, is 0.02036. So I'm going to leave it as 0.0204. Remember to round correctly. Okay, now this is where it gets trickier, should I say. What you've got to remember is that the sulfur dioxide, when it partakes in half equations, any reactions, you end up making sulfate ions. So it does these redox equations. Okay, so the sulfur is going from an oxidation state +4 to +6. So this means that the sulfur is releasing 2 electrons, and the question up here tells us that it is a reduction reaction with sulfur 4 oxide. Okay, so how do we use this? As in the previous example, calculate the number of moles of the amount of electrons. So your number of electrons is being released by sulfur is 2 times 0.0204, which equals 0.00408, and then the number of electrons for being absorbed by vanadium. Well, we say that we have 0.0408 divided by 0.0400 comes out at 1 vanadate per electron, or 1 electron. Sorry, it should be the other way around, so that the number of electrons divided by the moles of vanadate, so it's 1 electron per vanadate. So in actual fact, going back to our original question, which is calculate the oxidation state of vanadium in the solution after reduction, because each vanadium has absorbed or received 1 electron, therefore final oxidation state is vanadium is +4. Remember, for oxidation state, sign before number. Okay, I hope you found this useful.